So let's start. So I posted the homework on Canvas. So if you have any question, you can email me. You can also attend the office hour on Friday every week. So the AI can answer your question. So as you can see, as you may already see in the homework. So the problem the problems in the homework are during the class. Only several parameters in the problem may change. We also have some review class before the midterm and the final examination to review those problems. And those problems will also appear in the midterms and the final examination. So make sure you can understand all of them. Those are very important for the examination. So today we will talk about the truth table and the CMOS. So in last class, we introduced the logic gates and or not. So here is one example for AND gate. So you can see and one output logic gate. Here is a 3 inputs. One AND gate. You can see based on that row. N is the input number. So this is the Boolean algebra. Of course, the simplification, the selection of the gates are parts of the process named synthesis. Because the synthesis is so complicated, it's impossible for human to do that. So people use the software, so-called EDA software, electrical design, some short for electrical design something. So when you write, for example, a convolution neural network accelerator. Compared to the C, when you try to implement something by HDL, the EDA company don't provide. The synthesis, simplify your logic. Select the different types of gates to minimize the power consumption. Area beforehand, gate number, the number of gates of your design, and then eventually you will why you buy something. That is just description. Explaining which gate connected to which gate. So you eventually you will have something like that. And then you can simulate. And of course, you can specify some clock to your signal, so that your signal can change during that, in that clock, with that clock. Basically, this is the process. The synthesis process can happen on two platforms. The first one is into some bit stream, and then download that bit stream to one FPGA, so that the FPGA can run all into some application specific circuits, which is the real hardware. So here is the FPGA. The structure of FPGA is each connected and of course, can be verified. Let's say 1K by. So that you can construct a complete lookup table. So we introduced the so-called the canonical form in last class. The canonical form includes two types. One is the so-called sum of products. The other is a product of sum. And of course, so each product go in the truth table, which can generate a one. For example, one. Because for this A, B, and then we have five. After we have the simplified, and the gates. So you can see you don't yes. by those laws. I will introduce the algorithm which used by software at the end of. So at least the canonical form algorithm convert algorithm. So generate one. And here we will convert this piece of circuit. Here, like we convert the truth table to the Boolean algebra and then convert the Boolean algebra to the circuit. Here we convert the circuit back. Like X and Y. We can first write final results. So setting some intermediate variable actually can help you break the problem into multiple pieces. And then here we so you can see that the truth table, the Boolean algebra, and the circuit are equivalent. So we just introduce the how to synthesize the truth table or the logic on the FPGA. You just directly store the truth table and do the lookup. That's simple. Here, I will introduce how to do the real hardware part, the logic gates part. So the dominant type of logic gates, now we talk about fabrication, talk about how to fabricate a chip. When we talk about this, we actually mean the CMOS. The CMOS is why and the real fear of but you can view these CMOS as each type as but the stage is open. So and the difference and of course, there are But to build a gate, we need them both. Logic gates, we need them both. Logic gate, like a NOT gate, or AND gate, AND gate, or OR gate. So we use the NMOS. Because it can pass the one back. I will give you some example for this pull down and pull up network. And of course, the simplest logic gate is and one of this. So you can see from this figure, we have one PMOS. And then we can do some analysis. You have 0, 1 output. You apply 1. When the input is 1, then the output is 0. So you can only connect it to the ground or the VDD. Either one on otherwise and this pull down network and pull up network can help you to achieve that. And this is a complex example. It includes two PMOS and two NMOS. And this gate is so-called a NAND gate. I draw the and then I so A when the A is a 0, B is a 0. And both but for the bottom down why. The same thing you can try with one. If A is 1, B is a 0. B is a 0. A is also B is also one. If one of them is open, then the one. On the other hand, equals parallel. So one any of them. So the y is 1. Yes. That's right. So here is a very complex example, and by this example, you can learn how to build a so the first of that is and put out network actually implementing So the first step. So we can apply the local law. Here, let's see. And when you do this math, how B and I. After that, all right. Then you have A bar, A off, because it's all. Yeah. So B bar B bar. Network implement that F, not the complement of F, but the F itself. However, invoke a law. In each step here, I apply a invoke law. Why function? Because each and you can see a bar above all the variables. So you can use the C bar, B bar, or A bar, or B bar. You can directly send the C signal. So first we need to and you can see this is the end. And then you implement this. and eventually. So for the unknowns, like model law and then you can do the implementation. So we have this De Morgan law relationship. C bar multiplied by C and the relationship between them are you can convert this part. Yeah. And this part, for this part and this part. Yes. You don't have which
Live we have group back
yeah. Yeah, this is very because you don't want to connect really you don't want to connect you just want to so by one by itself and the negation of itself by A, I'm sorry, by C plus B. This is the bottom part. And this one is the top part. Either A is true, all A bar is true. Only one of them can be true, right? So only one connected to the output. It's impossible for A and A bar both are simultaneous.
So after C box.
It's so yes, it's corresponding.
Okay.
So now you can see how the synthesis happens. Here we just talk about the so-called ideal gates, but in a real world, the gates have resistance and capacitance. The resistance and capacitance will introduce power consumption and latency because you have a RC delay and the power from each gate. So, including length width and height. Because of the resistance. And the time is so-called RC delay. Typically, they call it. Here they build a RC model for the knot. The gate has some parasitic resistance and capacitance. So the gate is not perfect. It has some delay and power consumption. And you can estimate the delay like by these. And then we will talk about power. So the power has two parts. One is the so-called dynamical power. The second one is the static power. For the static power, when you turn your computer on, no matter you use it or not, even if it's idle, you still need to pay power consumption. That's so-called static power. But when you run some very heavy applications, you need to pay the dynamical power. And this is the by this equation, we can see that if you have a 4 gigahertz CPU, then the dynamical power will be higher than the 1. Because the frequency is larger. And static power, so now the power consumption is the major constraint, major limitation for your CPU. Because nowadays your CPU can reach maybe 80 watts or 90 watts. Further improving the frequency is not a practical way to make your computer run faster. And nowadays, people talk about new process technology, the so-called new process technology. That's the reason why the CPU can improve its energy efficiency at a more advanced technology node, generation by generation. So here is one example to calculate the total power consumption. The first part, and then we got get the final results. But I would like to remind one key, minor. So after you have the gate, you can do the synthesis. Network of those gates. And the gate network is actually used to implement your logic. For example, if you want to implement an adder or a multiplier, then this is the adder. By considering the power and latency. So when you write a VHDL, you didn't consider the gate latency or the power consumption. This is so-called functional simulation. You just prove 1 plus 1, letter 1 plus 1 equals 2. But when you do the synthesis, when you map those gates, you have to see how to decide the frequency of your circuit. But you never consider frequency during the functional simulation. The CMOS gates, the physical gates, becomes more and more important. Why? Because they simply decide your battery lifetime and your mobile phone cost. This example is a real example from Apple. So the Apple company just saying but because of the production throughput problem, they have to spend the same design. Because these two companies have different logic gates, AND gates, NOR gates, NOT gates, different physical gates. And those gates are industry. So they have to implement the state. And then you have different so that's the reason why the same design, even the same design, will achieve different battery lifetime if you sign the same design to different fabrication companies. So the CPU, the chip size matters a lot. People favor a smaller chip size. Why? Because they need to fabricate the chip. And the system size is the same smaller CPU size means at the same time is in the same area, you can have more CPU. Assume that we have this of then your chip is $100. One chip is $100. If I can fabricate 10 chips, so that's the reason why we want to have a smaller chip area. Besides the, die prices, you also have to consider the defects. When we do the fabrication, the die will have some defects. Assume we have the same the same position. So on this one single die, we have 4 defects. Then we have more good chips. If the chip area is large, then we only have 1. Considering the defects, then we have a stronger motivation to make the chip smaller. Particularly because now the transistors are really small now, so the defects are you will have a lot of defects, and the yield of the chip is maybe only 20% or 30%. Smaller chip area can help you to achieve a higher yield. Any question? If no question, we can stop today. Thank you very much. Yes.
So we're gonna take your usual draw that we complement, and so each of those we're going to do all the floors parallel.
Yes.
And how would you like which you can do? Or just a done. Like, why is it a? Why? Right. So, like, why is it that? Oh, yeah, I see what you're saying. Okay. Okay.